Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the great stuff. This is part of the good stuff. This is the AAS Journal Author Series. And I am very happy to have Jessica Werk with us today. Hello, Jessica.
Hi,
Let's see. It is October 9th of 2024 as we record this. And Jessica, what is your geolocation? Where are you at?
I am in Seattle, Washington, and in particular on the campus of the University of Washington.
Very
And
nice.
yeah, it's a beautiful day here. It's sunny. It's
Whoa,
usually,
cloudy.
well, it does start to rain soon. Usually Halloween is the turnover point in Seattle where you can expect really dark, kind of rainy weather that's excellent for eating soup and
And
wearing
crackers.
wearing good, yes, and wool coats.
Unfortunately, I do live in Phoenix, and I would say even by October, we will not be in coat weather. So I can say that pretty confidently.
You're never in cold weather, I don't think.
Well, sometimes in like January, February in the morning, it will get around freezing, but then it, warms up till 80 in the day. So, it's
Okay.
limited.
It rarely gets below freezing in Seattle. We'll have
Yeah, yeah.
maybe in like February a week where it touches freezing, but that's, as low as we go temperature
Cool.
wise.
Cool. Well, actually, I am planning on being out at UW at the Institute for Nuclear Theory probably in February of this, February, March, I'll be out.
Just on the fourth floor of the same building.
Yeah, right.
Stop by the third floor
I
and
will
say
pop by and we'll
hello.
say in 3D. We can greet each other in 3D. That'll be amazing.
Yeah, here at the astronomy department at the University of Washington, we have a beautiful image of the Andromeda galaxy right where you step off the elevator. So,
Dude, that's very cool. Very nice. And speaking of Andromeda galaxies, Jessica, what do you like to do for research?
well, I have a whole lot of interests when it comes to astrophysics, but lately what piques my interest most is diffuse gas. So atoms in the most diffuse phase. And so, if you consider the known universe in terms of non-dark matter, non-dark energy, the baryonic component of the universe, the
No.
vast majority of the baryons in the universe, 80 to 90% of them are in this diffuse gaseous phase. So if you
Yep,
care about matter that we can observe, then I think that you should care about gas.
absolutely. Very cool. Boy, that was compelling. I'm going to change fields now.
And okay, so most of the gaseous material in the universe is actually outside of galaxies. So
Mhm.
it's not inside of the interstellar medium, which is a rich, beautiful, multi-phase medium of galaxies that, drives galaxy evolution and does wonderful things. I love the interstellar medium, but I have been focused on more rarefied gas, say in the circumgalactic medium or intergalactic medium.
Very
And so
cool.
that's my main interest. I count atoms in intergalactic space.
Awesome. And that is going to bring us to this very lovely APJ supplement article. It is open access. It's the open access era, people. You can go get a copy for free. Go get one.
Please go get one. Yes.
Please go get one. There we go. The Plain Quasar Survey. First, data release. And Jessica, take us away.
Well, first, I'd just like to start out by acknowledging all of my amazing co-authors on this manuscript and the Plain Quasar team, which is Dr. Kryl Chernyshov, who was a postdoctoral scholar here at the University of Washington and has since actually moved on to being a climate data scientist with the Rocky Mountain Institute,
All
doing
right.
amazing work. He's
Okay.
still engaged in some of this work. We occasionally Zoom and talk about plain quasars. So, Dr. Hannah Bish, a graduate of the University of Washington and now a postdoctoral scholar at Space Telescope, Dr. Young Zhang, a professor at RPI, and Mary Putman, a professor at Columbia University, Josh Peak, a scientist at Space Telescope, and
Yep.
Dr. David Chiminovich, another professor at Columbia. And all of these people were deeply involved in the survey from its conception to its execution to some of the follow-up studies that we're doing.
Great shout out. Great shout out. All right. Let's get into the Plain Quasar Survey. Here we
And
go.
so maybe it's worth saying that we've also been involved. This collaboration has been involved in a few other projects, and so The way this kind of started was actually with Dr. Hannah Bish's thesis work, where she did a survey called Quasar. And that's actually on the next page. We reference this Quasar survey in the introduction. And the reason, and so you can see right there, where, oh, the top paragraph there.
Yep.
So the reason I think that this arose was that we really wanted to see if the Milky Way had a rich multi-phase circumgalactic medium like that of its, brethren L-star galaxies in the nearby universe.
Okay.
And so we designed the survey, and one of the reasons it's difficult to look at the circumgalactic medium, the atmosphere of the Milky Way itself, the extended atmosphere, not the ISM, that extended atmosphere that's like, diffuse material throughout the halo of the galaxy. One of the reasons it's actually really hard to see that is that we are embedded inside of the interstellar medium of the galaxy.
Yes.
And so when we do the kinds of experiments that we do, which are usually absorption line experiments to see very, very diffuse low density gas,
Okay.
we use these background sources to do it. But the ISM is a really confusing element in that because it kind of swamps it. It's more dense, and you have to figure out a way of acknowledging and maybe subtracting out the interstellar component to
Okay.
figure out where the circumgalactic component is.
Okay.
And we had envisioned a couple years before this what's called the Quasar survey, which paired bright background quasars with stars in the halo of the Milky Way with known distances. So we use blue horizontal branch stars as standard candles.
Okay.
And Hannah Bish kind of pioneered this subtraction technique where these things are very close in projection, so they're paired.
Yeah.
And what you can do is the blue horizontal branch stars maybe 5 kiloparsecs from the disk. You have a spectrum toward that. You have a spectrum toward the quasar. And then you can subtract off the spectrum from the blue horizontal branch star from the quasar. And what you're left with, you think, is the circumgalactic medium of the Milky Way.
Uh-huh.
Well, Hannah did this work with the Hubble Space Telescope Cosmic Origin Spectrograph as part of her PhD thesis.
Cool.
And what she discovered really puzzled us. We focused on this carbon-4 absorption line, which is a highly ionized line. It was one of the ideal doublets to look at.
Uh-huh.
And when she did this subtraction technique, we found that the Milky Way circumgalactic medium did not have as much carbon-4 as other L-star galaxies seem to have by a lot. It was very
Okay.
deficient in carbon-4 compared to other low redshift star-forming galaxies of its same mass.
Okay.
You would have expected an order of magnitude more effectively. And this troubled us. It's always been a question that people had, and I think it's a really, really interesting result. It's for plenty of reasons, but one of the reasons we thought was that the data that we used was all at very high galactic latitudes. So
Oh,
it's basically all looking straight up from the disk of the Milky Way. When
okay.
you look at other galaxies, your sight lines, they'll go through the plane of the disk the
Yeah.
vast majority of the time. And so if a lot of the circumgalactic medium is kind of concentrated on the disk plane, a large fraction of it, which isn't totally outrageous, actually, based on some other, extragalactic experiments, we would have missed it. And we would have missed it in part because there really aren't a lot of quasars along the galactic plane that we know of.
Okay.
And so meanwhile, David Shimonovich and Mary Putman at Columbia University were having a conversation about what to do with some of the Galax cause data that they had, which was the kind of end of life survey of Galax, which was done in just the near ultraviolet bands and primarily looked at the plane of the Milky Way. So
Okay.
there's these beautiful Galax cause data. And it turns out when you combine that with some of the other kind of large all sky surveys like WISE and Gaia, you
Mm.
can actually perform these photometric selection techniques for quasars. And David Shimonovich was saying, are these interesting? Is it interesting to find quasars in the plane of the galaxy? And David was asking Mary, and Mary was like, actually, I think it is. You should talk to Jess Werk. She's very interested in this. And so we all started talking and we were like, yes, that is very interesting. We would love to have quasars behind the plane of the Milky Way, in part to test this idea of, is the Milky Way different from other L-star galaxies? When we finally look on the plane, do we see as much carbon-4 as other galaxies have?
Yes.
Um, And, also because we always need more UV bright quasars in the sky because they're incredibly, fruitful sources for looking at very low density gas. They're some of the brightest sources in the universe at these large distances. And so it's just a nice path length to look at. So
Cool.
we undertook this plain quasar survey. And what it involved actually, so you see in section 2 here, we start talking about our photometric selection.
Mhm.
And this was really the work that David Shimonovich had begun at Columbia University. And we just kind of streamlined in order to publish in the paper. But we had a number of color selection techniques using WISE 2 colors,
Yeah.
using confirming that sources weren't super local using Gaia parallax. And we correlated with other, surveys of quasars and performed similar kind of selections that these other surveys did. We actually had 2 different photometric selection techniques that we used.
Okay.
And one really identified a very, very low galactic latitude sample at less than 10 degrees. This is this
Ooh.
first one that you're
Mhm.
that you're highlighting here.
Mhm.
And then the next was really just expanding this to an approach similar to the UVQS survey, which was led by Monroe in 2016. And we did a WISE color cut and using the Galax cause just near UV colors and found a whole other host of quasars less than
Ah,
about 25 degrees. So when we say low galactic latitudes, we're talking about galactic latitudes. And this is in the galactic coordinate space, right? Where you've got the center of the galaxy as the center of your coordinate rest frame.
yes.
And then the galactic latitude is how far off the plane you are. So we're looking at 25 degrees and lower.
Okay.
So behind the plane of the Milky Way, effectively.
Yes.
And maybe you want to scroll to figure 2, just to kind of illustrate exactly what this sample looked like and how it really was, I think, a huge advance over what exists in the archives. And so on this figure, there's a lot of points on this figure, so I'll walk you through it. But the very background of the figure is the H1, all sky H1 from the H1 4Pi survey. That's H1 detected in 21 centimeter emission at velocities greater than 80 kilometers per second relative to the rest frame. So in
Okay.
this frame, the center of this is the center of the galaxy. The galactic plane lies along that 0 degrees galactic latitude.
Mhm.
And the reason it doesn't show up in this image is that we basically subtracted it out. It's not high velocity H1.
Right.
We're not including that. So what you see in the background is kind of the beautiful high velocity sky of the Milky Way that shows some of these gaseous structures moving in the circumgalactic medium of the Milky Way. And in particular, if you look at these low galactic latitudes, you see the Magellanic system that cluster around, minus 45 galactic latitude with galactic longitudes around 270.
Okay.
And so you see that beautiful Magellanic system with a stream trailing behind it all the way in the south that covers a huge fraction of the sky. Yep, that's just down there. Yep, your cursor is right on the Magellanic system. And then behind it, if you
Yep.
trace, that lower bit at very low latitudes, that's the Magellanic stream. And
Very, very
it's
cool.
it's this, set of interacting galaxies with themselves, interacting with the Milky Way. The Milky Way is cannibalizing them. The gas is getting stripped from behind. There's just a ton of stuff going on there.
Mhm.
And that's probably maybe 50 kiloparsecs from the galaxy. So that's actually a huge fraction of the Milky Way's circumgalactic medium, it turns out.
Very
And then there are these other really well-known structures. And so this is just to kind of guide your eye on where we're looking. And so the
okay.
black and gray points are some of the archival data that exist. And you can see the distribution of those. They're UV bright quasars. The
Okay.
UVQS survey, which was, really just foundational for telling us where are UV bright quasars in the sky. And then this COSCAL survey that was led by my collaborator, Dr. Yong Zhang, which showed, the high signal to noise UV quasar data available in the Space Telescope archives. But what you can see when you look at just the black and the gray points
Yep.
is that there's really not a lot below galactic latitudes of 25 degrees,
Yep.
right?
Yep.
And so all of those purple points there are the plain quasar candidates in some form or another, right? Like purpley, reddish, magenta, whatever, the colored.
Right.
And so, this is the different colors tell us what types of sources they are and if we got spectra of them, because you do a photometric selection of quasars, but they're not confirmed as quasars until you get an actual spectrum.
Yep.
And we think that that's really important for our colleagues that are, writing telescope proposals with the Hubble Space Telescope. They want to confirm that they're actually looking at a quasar like they think they are, because otherwise it'll be a disaster for their experiment.
Yikes.
So what you can see here is all the plain quasar candidates. And then,
Right.
one of the things that we had to do was spectroscopic confirmation of these 305 candidates. I believe it's 305 plain quasar candidates. And
Right.
so, and you can see the ones that are confirmed to actually be quasars in the end of what we did are these dark purple diamonds.
Yes.
And what we did was we just confirmed a large number of UV bright quasars at very low galactic latitudes where the archives really just didn't have any coverage.
Very
And
cool.
I think for us, it's something that was going to be very useful. And I can talk about some of the future work we're going to do with this to test some of our
Into
hypotheses
that.
about the Milky Way CGM. But at the same time, a number of people working in this field of diffuse gas who love to do quasar absorption spectroscopy, all of a sudden they have new targets to look at to see if they're, paired with serendipitously paired with galaxies nearby in projection that they might look at circumgalactic medium there. Or maybe they're doing an IGM survey and it goes through, a large filament that they think would be really interesting to study. And so
Right.
what my hope is with this survey is that other people will simply use it. All the quasar. And so if you go to the tables in this paper, what we've done is we've really tried to make it accessible for people.
Mhm.
And in particular, all of these data are now available on the Mikulski Archive for the Space Telescope, or
Big
MAST.
shout out. Big
Uh,
shout out. Yep.
and so you can there's a website in the paper that you can go to, and you can see all of these tables with everything if you go to the online article, including the galactic longitude and latitude, the magnitude from Galax cause,
Yep.
optical magnitudes that we derived from a number of different surveys. We did a deep dive on archival searches, and you can see some of these targets from plain quasars were actually known to be AGN previously. It's just
Yeah.
that they weren't known to be UV bright quasars. They didn't necessarily all have spectroscopic redshift confirmation. And yeah, so we
Pretty
list
cool.
all the archival discovery papers in here, which come from, like I said, a whole range of different surveys previously.
Mm.
And we've also discovered a number of very brand new quasars that we went after and got spectroscopic redshifts for.
Cool.
So table 2 in this paper tells you which targets were confirmed. And okay, so that leads me to this redshift confirmation part, right? So getting redshifts for quasars, and in particular, very precise redshifts, is
Yeah.
actually pretty challenging. And we did it in a couple different ways.
Okay.
Just Sorry, do you have questions? If you do you want to ask questions? I'm talking a lot, I
No,
realize.
I'm with you. I'm following you. It's
You're
great.
following me?
You're,
All
you're,
right, great.
you're rolling and I'm with you.
I'm rolling. Okay, yeah, it turns out I can talk forever about this. So
It's great. Great. Beautiful.
but we
Beautiful.
did these two different redshift determinations where we just used some of the narrow lines
Mhm.
and we used all of the lines available to us in this kind of template fit. And that's this Mars utility that's freely available. I forget what Mars stands for, MARZ, but manual and automated redshift software.
There we go.
And I will say that it was great because it's just a little web application. You can upload your spectra, you can
Nice.
tweak which templates you're using. I really enjoyed using Mars. And in particular, I had a question at one point about the reference wavelength of the templates, whether it's vacuum
Yes.
or not, and so or air. And the PI of Mars actually like got back to me instantly and was like, actually, it's vacuum. So thanks for asking. Anyway. anyway, so very helpful, very easy to use tool. And the narrow emission lines we just fit with kind of Gaussians in the spectra,
Yeah.
and we took
Mhm.
a centroid wavelength and determined a spectroscopic redshift that way. So if you scroll down, figure 3, I think, is just showing all of the spectra that we obtained either with Apache Point Observatory 3.5 meter or MDM 2.4 meter. We
Nice.
also used the MDM 1.3 meter for a couple of them, until we realized some of these were faint enough we were going to need a larger
A little
telescope.
bigger, yeah.
But we do have one of the 1 point. I do this to just kind of like show you an example of what we get. And the redshift of the quasar is given on the top of these plots. And then
Mhm.
those pink lines are kind of highlighting what the redshift solution tells you where you should expect some lines. So in that first MDM 1.3 meter one, right? You can see some broad lines from H beta and O3. You
Yeah.
vaguely maybe see O2. Maybe that's consistent with O2 being there.
You're stretching
And
me on
but
that one, but
you
okay.
can you can see how the redshift determination might be a little hard given a spectrum like this because these
Yeah.
lines are really broad.
Mm.
And so for this one in particular, right, there's a Mars redshift. You can't really get a narrow line redshift because there are no narrow lines available. We might have used the O3 line as a narrow line, but it's actually still kind of broad and noisy.
Yes.
And so, we really tried to be consistent about our errors and what we think, and it's probably about 200 kilometers per second. Even though the spectrographs themselves that we used on APO and MDM, in theory, you should be able to get to a precision of like 35 kilometers per second or 70 kilometers per second.
Okay.
Uh, the broadness of those emission lines from the quasar itself and the accretion disk around the quasar give you this larger uncertainty in your redshifts. But
Yeah.
you can see some of these spectra are really beautiful, like the APO 3.5 meter one just below at 2.63. And there's a
Yep.
nice narrow line
Yep.
of O3 there,
Yep.
and then the broad lines.
Yep.
And then you can see, some of these are different types of AGN, right? Where you've got the MDM 2.4 meter, you've got the beautiful narrow lines of the 203 lines, 5007 and 4961, I want to say, 4950, 4959. Anyway, I don't carry that around in my head as much anymore, but it's something like that. But and then you can see
Yeah.
in one case, at the APO 3.5 meter on the lower left-hand corner there, that really high redshift quasar, right? Where we're seeing
Right.
maybe not O2, but it's just like a single line of magnesium 2 emission that
Sounds
it's
clear.
consistent with. And that's where the like quasar templates come in handy because with these, when you're doing spectroscopic confirmation, you don't know what redshift you're going to find. And sometimes you get stellar spectra, which I'm not showing here because those are less interesting to me. We have some M stars though.
Okay.
If you're into M stars and you're watching this, we've got probably like 30 confirmed M stars and nice APO spectra of them.
Cool.
And they're all downloadable from the mast. If you want those spectra and want to do kind of M star stellar astrophysics, I'm sure there's something cool to do with them.
Sure.
Uh, I'm not going to use them, but generally, all of the spectra are also available to download on mast. And
Oh,
so
okay.
um, this is something that I feel
Cool.
really passionate about, which is like open data and data releases. And so my hope is that anybody kind of reading this paper can be like, wow, that quasar is exactly where I wanted to be. I need the spectrum of that quasar. I really want to know its coordinates. I want to know all about its archival information. Just go to the MAST DOI and grab it for yourself.
Awesome.
Um, and so, yeah, I like to do things that are kind of done in a reproducible way. So now if we
No
scroll down to
argument
figure,
for me.
yeah, if we scroll down to figure 4 here, which, again, this paper is just telling you about the data and the redshifts that we found. But you can see this is kind of telling you the two different methods of fitting redshifts. So there were some of our plain quasar survey that had some redshifts available in the archive. Some of them were uncertain. Some of them, they weren't clear on exactly what
Okay.
they used, but we decided to just compare what we got from our Mars template fitting method
Mhm.
with the archives and from our narrow method with the archives. And you can
I'm with you.
see given the uncertainties, we thought they were around 200 kilometers per second. We're pretty consistent with the archival redshift estimates. There are a few really strong outliers here.
Yep.
And I
Yep.
actually discussed those in the paper. A couple of them, they were only given to two significant figures of precision in the archives,
Uh,
right? So like
uh,
1,000-ish kilometers per second or more uncertainty. So the fact that they're different shouldn't like raise any red flags. But again, this is just for people to understand what our redshift estimates are
yeah.
getting us and how accurate they are. And you can see, I
Uh,
don't think that offset from Mars and archival is significant, but you can see that when you do look at just the
yeah.
narrow lines, which probably give a slightly more accurate actual redshift of the galaxy itself. If it's narrow, it's not coming from that, broad line stuff that's really uncertain to
Yeah.
determine a redshift.
Yeah.
So yeah, and
Cool.
when the narrow lines are available, I think that they probably offered a slightly more accurate picture of the redshift
Yeah.
of the quake. Um, but again, if people don't like the way that I determined redshifts in this paper, they are absolutely welcome to download the spectrum and use their own favorite, quasar redshift tool to determine those redshifts themselves.
Okay.
Uh,
Very good. Very good.
and yeah. And so, I mean, this is basically the paper, right? It's just a huge data dump of the 305 plain quasars and all of the 165 that are now spectroscopically confirmed. I
Okay.
will say that we'll probably pursue spectroscopic confirmation of the remaining plain quasars using APO. And
Okay.
so we're submitting proposals to do that. But again, I gave all the coordinates of these candidates, and if anybody else does spectroscopic confirmation, that would
Go.
be great. Happy for that work. And then
Absolutely.
I'll talk a little bit more if you're ready for me to talk about it, about
Sure.
what we're already doing with some of these plain quasars and what you can expect to see soon.
Let's
Because
let's save
if,
that. Let's save that till we get to the future.
sure,
Let you roll.
sure, to the future. Yes.
Yeah.
Okay. So again, this is the paper.
Very
Uh,
cool.
and uh,
I
and yeah,
understand.
I think the last shout out I want to make is to UC San Diego for hosting me for my quarter-long sabbatical last winter. Um, and this was when I was really able to write this up and publish these data and get the data released. And that's what it took for me to do that. And also just generally, for any being faculty at a large university is challenging, and you really prioritize your work with students in terms of teaching and mentoring, and it's wonderful and rewarding, and getting papers out yourself is like almost takes like a
Extra.
sabbatical, but also takes support. And one of the things that I do with my friends and colleagues, professors at different institutions, Laura Chomick at Michigan State and Kate Rubin at San Diego State University,
Yep.
is we had these kind of regular weekly meetings where we just hold each other accountable. And for an hour, we sit and write. And just doing that for an hour, even once a week, helps you get a paper like this out.
Yes.
And so yeah, that's important to acknowledge.
And I will
Yeah.
definitely give a shout out to Margaret. So, yay, Margaret.
And to Margaret Burbage. Oh my goodness. There's this beautiful program at UC San Diego that honors Margaret Burbage with women in physics coming to actually the new astronomy and astrophysics department at UC San Diego.
Yep.
And yeah, it's just wonderful. And it was great to be there, and it was a great working environment.
Awesome. Awesome. Very good. Beautiful work. Beautiful work, Jessica. And I want to thank you so much for walking us through this first data release of the Playing Quasar survey.
My pleasure.
Sure. And so you definitely touched upon it there. And so let's go ahead and go there. And where do you think that this work goes from here? Can we get another 1,000 candidates? Can we do spectroscopic follow-up of all of those? And just sort of next steps. And right now, as you said, this is more or less a data dump. And so how about the interpretation of what we currently have before we get more? And so just sort of next steps, where do you think we go with this over the next couple of years?
Exactly. So Where we have already gone with it and where you can expect to see some papers is what we have with what we already know, right? And so we took some of these spectroscopically confirmed quasars that were at specific galactic latitudes and longitudes that were interesting to us from this Milky Way circumgalactic medium perspective of testing whether the circumgalactic medium really is along the plane. And so to do that, we had to do UV spectroscopy of
Okay.
some of our confirmed plane quasar candidates. And we did this with a cycle. Oh my goodness, I forget what cycle it was, but it was a couple cycles ago.
Okay.
Maybe one cycle ago. Anyway, we did this with the Hubble Space Telescope Cosmic Origin Spectrograph, and we have all the data. We've analyzed the data, and we're looking for this extended signal of circumgalactic medium in the Milky Way. And
Okay.
I am not going to actually tell you what we found. We have two really, really interesting discoveries in this new discovery space that we opened up with the Plane Quasar survey. One is focused on what is the Milky content of the Milky Way CGM along the plane
Yes.
and what it's doing. Is it a co-rotating disk or not? And the other one is a totally new serendipitous discovery that we were not expecting at all, but it's only because we were able to look at these low galactic latitudes in this
Yeah.
certain region that we were able to see it. And I'm not going to tell you what that is either, but there are Kirill Chernyshov is leading that Milky Way CGM paper, and a graduate student here at the University of Washington, Bonnie Choi, who actually just got a paper published on the archive, not on the Plane Quasar survey. She'll be putting it out on the archive soon. She just got a paper accepted on the Milky Way CGM, something else in the Milky Way CGM, looking at metallicities. But yeah, so Bonnie's doing great work. So look out for a paper by Bonnie Choi and Kirill Chernyshov. And we also have some work that we're doing with simulators. And so there's a graduate student at Columbia University, Michael Messere, who's working with Greg Bryan and Mary
Right.
Putman.
Right.
And they're looking at the CGM of Milky Way-like galaxies in the illustrious TNG
Okay.
simulations.
Okay.
And they're going to be comparing that with our Plane Quasar data from the Hubble Space Telescope program. And so that's a really mature piece of work that'll be coming out soon too. And so then you said, where do we go next? Are we going to find 1,000 more quasars on the plane? I think for me personally, there are so many quasars along the plane now that we haven't looked at that I'm focused on, making sure we can confirm the rest of that
One voice.
sample.
Yeah.
So 140 or something, 45 more quasars, 145-ish, 140 more quasars, 140 more to observe with APO. We'll see if we can get them. Some of them might be in the Southern Hemisphere, so maybe not accessible by the APO observatory. But we'll do some more spectroscopic confirmation. But for now, I'm just really hoping that people will use these quasars. And in fact, actually, another group at Space Telescope Science Institute was doing something with the circumgalactic medium of the Large Magellanic Cloud.
Okay.
And now there's another approved space telescope program using our Plane quasars as background probes. So I'm just hoping, like I said, more people will use them to do really exciting science, and it would just make me so happy.
Well, I'd like to make you happy, so that's pretty good. That's fantastic. So that was quite a number of teasers there on some future articles. So do check those out when they come out, people. And yeah, I think it'll be really exciting over the next couple of years to see people make use of this data set, and as we further characterize it and let us know what it tells us about the intergalactic medium. It's awesome.
Thank you. Yes, I think it's awesome too.
Very cool. Jessica, thank you so much once again.
My pleasure. This was really fun. And
Yeah,
thank you so much for having me.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.